Bismillahirrahmanirrahim. So this lecture is about CMOS fabrication. About CMOS fabrication, and in the next part we will talk about the layout. So what is fabrication? Fabrication is basically the physical manufacturing of transistors and all your circuit on the silicon wafer. Okay, and the wafer is sort of both a mechanical and electrical support for your whole integrated circuit. So the process by which this is done is called lithography or photolithography. We will see in the upcoming slide how the circuit is translated, is transformed onto the silicon. And in particular, two views are important to understand. One is the top view. If you are looking to the silicon from the top, and the other is the cross-sectional view, in which if you cut the silicon through the middle and see what's inside this. So we will have a look at both the views and try to understand how things look like. Okay, so this is a nice picture which shows that how the light, ultraviolet light, is used to transform your circuit. So here is the mask. Okay, and this is a capture of your circuit. Okay, and it has like these areas which allows the light to pass. Okay, and after passing they go and they hit the silicon wafer, and it is like printing. So you just put inside the paper and you print things. So you just put the silicon wafer, you have the mask, and you pass light over the mask, and the circuit is translated onto the wafer. Okay, so let's look at an inverter circuit in some more details. So as you know, the inverter circuit, this is the PMOS, this is the NMOS. Here you have your input, here you have your output. Okay, and let me use a different color. For example, this one. This is your source, this is drain, this is source, this is drain, this is source. So the source is connected to VCC and ground. Okay, so this is the CMOS inverter, and on this side you see the whole layout. So if you look at this, here we have the NMOS and here we have the PMOS. So we start with the P subtract, which is like our first thing. It is like mechanical support for the whole thing, and we start to develop different areas. So for example, we have this area which is our doped area, and it has abundance of electrons. So N plus means abundance of silicon. So it is an NMOS, and this one is the drain. Okay, and this one is the source. So you see the source of NMOS here, it is connected to the ground. So here we have the ground, and it is connected to the source. Here we have the drain, and the drain is connected to the drain of PMOS. Okay, here we have the source of PMOS, and it is connected to VDD. Okay, and you see these are the gates. So this is the gate and this is the gate. The gate uses something that is called polysilicon. Okay, so it uses a material that is called polysilicon, and you see for different materials we have this sort of legend which explains which material uses which terminal uses which kind of material. So we have N plus diffusion, we have P plus diffusion, which are these. Okay, and we have this N well. So what is this N well? The N well is like a housing for the PMOS inside your P subtract. So the N well is like a housing for your PMOS inside the P subtract, because both PMOS and NMOS uses different kinds of substrate. So in this way, by using the concept of wells, you can fabricate different kinds of transistors. By different, I means both the NMOS and PMOS in the same material. Okay, so just to be sure, I can draw these lines. So both these are your terminals. Okay, they are the gate. Okay, and these are your inputs, and your output is this one. This is Y. You see, this is Y, which is your output, and Y is basically shorting the drain of PMOS with the drain of NMOS. So this is the layout of the CMOS inverter. Let's go to the next slide. And so there was this question that where is the fourth terminal of the transistor. So normally whenever we just say this is the source, this is the drain, and this is the gate. But actually there is another terminal that is called body terminal. Okay, and this is different for N type. This is a P. For NMOS this is a P type material, and for PMOS it is an N type material. And normally we do not draw this terminal because it connects to either VDD or to ground. Okay, and we just don't show it. But if you want, it is here. It is here for NMOS and it is here for PMOS. This slide uses a sort of slight different colors to show the prominence of different gates. Okay, so this is the same thing, but it uses like different colors to emphasize different terminals and all that. This is the top view. So this is the second one. So until now we were looking to the transistor through a cross-sectional view, and now we are looking to the transistor from the top. Okay, so you see here is your VDD line and here is your ground. Okay, and we have this different kinds of, so this is our input line. So here this is the polysilicon. Okay, you see it is the legend for this. So here is your input, here is your output. On this side we have the NMOS, and on this side we have the PMOS. Okay, so this is the same, but we are looking from the top. So the same color code is used for showing the different regions. But one thing that is new is, so for example, this is our N well. Okay, and these blacks are basically contacts. So it shows where two things cross. So these are the metal contacts. So for example here it shows that the VDD or supply is shorted with the source of PMOS. So it is basically showing this point. So we have the source of PMOS, it is shorted with the supply voltage. I hope that you can make a sense of other points. Okay, so here we have like the more detailed step-by-step process of the different kinds of masks. So we have the mask for N-well, we have the mask for polysilicon, for N plus diffusion, for P plus diffusion, for contacts, and for metal. So basically you have different kinds of layers in your IC. So you can consider it like a multi-story building. So this is one layer, second layer, third layer, and so on. So things are developed like in layers. So you see here the first one is the mask of N-well, then we have the mask of polysilicon, then we have N plus diffusion. So you see these masks are used to expose some areas, selective areas of the wafer. This is the fourth one, this is the fifth one, this is the sixth one. So you have to use different kinds of masks to develop different kind of region in the wafer. Here it is shown in more detail in a step-by-step process. So I will try to go over this in some brief details. So you start with the P subtract with the blank wafer and build a sort of this silicon dioxide layer. You see, you are just like cooking things. So it's like they are exposed to very high temperatures for the development of this layer. So you are on top of your P subtract, you develop this silicon dioxide layer. Then on top of that you develop this photoresist material. So this basically is a very sensitive, light sensitive organic polymer. It resides on top of your silicon dioxide. And what is the purpose of silicon oxide? It is basically to protect the wafer. And what is the purpose of the photoresist material? It is there to increase the sensitivity of the whole thing to light. Then you are putting your first mask. So this is the mask for N-well. Okay, and what you see is you strip off the photoresist material here, and all the other is same. So you have applied your first mask and you strip off some region to develop the N-well. After that you do something that is called etching, and you use this acid to clean things up. It only will take the whole structure here where it is exposed. Okay, so then N-well is formed by diffusion. So this is the process of a separate process. So place wafer in furnace. So here is the explanation of the process with arsenic gas and heat until atoms diffuse into silicon atoms. So this is arsenic atoms diffuse into silicon. So basically this shows the process of how you can develop the N-well. And N-well, you remember that it was used to house the PMOS. Okay, then you strip the so now the N-well is formed. So you strip the silicon dioxide layer. You see, now we don't have So we have removed Si2 is removed and photoresist is removed. So now we are going to the next step. You see, deposit a thin layer of gate oxide. So this is polysilicon, and again there is a whole process of doing that, which is called chemical vapor deposition. So people from chemistry can know the exact details of what is CVD. Okay, for us as electronic engineers, we are going through this material because we want to know how the ICs are manufactured, but actually the more details are related to the chemical processes and all those things. So but why we are studying these materials here, I will tell you, because we want to understand these things, and in the later in the course we will see that there are certain properties of how you develop your subtract and your circuits that affects your delay, the circuit delay, the circuit power consumption, and the circuit area. So as electronic engineers, we are after those three things. One is the area. We want to minimize or optimize the area. We want to optimize power. We want to optimize delay. So why we are studying this material? Because we want to see where we can optimize these three things. Okay. So the next one is the polysilicon. You apply the polysilicon mask. So this is the polysilicon mask, and you have, again, you put the UV light. Okay, and you see that only this polysilicon is developed and this is safe. On top of that, what you do, you apply a protective layer of oxide. On top of that, you provide a protective layer of oxide. So the polysilicon gate, basically when you apply the polysilicon, it serves, now this is important, it serves like a mask, and it allows the precise alignment of your source and drain region. When you do this, the next step, it will be like when you develop the source and drain thing, they will be perfectly aligned because of the silicon dioxide. Okay, so this is what that means. I'm removing this one. Okay, so let's go to the next one. The next one is the formation of N diffusion. So now you are applying the pattern to form in N plus regions. N plus region what there in the mainly in the NMOS. So okay, so when you apply the N plus diffusion mask, what happens that here and here you will have the development, and also here. So this was one N plus was in the PMOS. So you see that it is transformed like this, and then you strip off this material. So you strip off the oxide layer and you finally get this. So now we have all the N plus regions that are developed in the wafer. Now we apply the one other mask, so it is the P mask, and again there is this is your mask. You put the ultraviolet light, and it is transformed here, here, and here. Okay, so this is like the next one is the mask for contact. So you have the mask, you pass the ultraviolet light, and you develop these different contacts. So the contacts, I told you, are there to form the physical connections to, if you want to short two type of regions, you have to use the metal contacts. If you want to short your source to, for example, VDD or to ground, you need these contacts. Okay, so then we have the layer of the metallization layer. Okay, this is the mask or metallization layer, and again it is transferred like that. Here is the whole summary of the whole thing. So what we have explained in different slides, here are all the things in one slide. Okay, so no need to revise this material here. And this is again the next slide, which has the whole summary of all the things. Okay, so finally you have this NMOS, this CMOS inverter. This is the final cross-sectional layout. So here is the whole summary of the thing. You apply different kinds of mask, you pass light through it, and you go develop different stage by stage different things. So you develop, for example, the N well, then you develop the N-type regions, then you develop the P-type regions, and then you develop the contacts and all these things. So this is the whole process. And remember that what I have told you, that why we are studying this, because as electronic engineers we are concerned with what is the power, what is the delay, and what is the area of our CMOS circuit. These are the things that are very important to us, and we want to understand the whole process behind this, not in, let's say, a lot of details which are related to, let's say, chemical engineers, but we want to understand it so that we can better understand our goals, which are area, delay, and power optimizations. And in the coming slides we will see how we can use this kind of information.